All right, very good. I will begin. So, dear Father, we thank you for this day, for class not being canceled, and just help us to glorify you what we do this day, Lord. In your name I pray. Amen. Okay, so I hope you guys have watched the videos, right? I have just like a brief comment, then I'll take your questions about homework. So, if we have a linear transformation from V, right, to W, right, V and W over F, and let's suppose that V has basis beta, beta equal to, say, V1, Vn, and let's suppose that W has basis gamma, say W1 through Wm, all right? All right, so we're given a linear transformation to go from here to here, all right? And then I tried to describe for you guys in the video how we would calculate the matrix of such a linear transformation with respect to those given pair of bases, right? And so I'd just like to comment a little bit more on that. So we have a coordinate map phi beta, right? So the coordinate map of phi beta, it trades abstract vectors in V for column vectors in what? F, let's see here, N, right? And likewise, I have a coordinate map over here, phi gamma, and that outputs m-dimensional coordinate vectors for W. And then down here, we have left multiplication by the standard matrix of T. Well, not the standard matrix, but the matrix of T with respect to beta gamma. So this T beta gamma is matrix of T with respect to bases beta for V and gamma for W. All right? What does this notation L sub something mean? Well, sidebar, L sub A acting on X is by definition AX. So the point here is there's an association. We can take any matrix A and we can associate it with L sub A. So this would be say in F m by n, right? Oh, excuse me, yeah, m by n, and this L sub A, the fundamental theorem of linear algebra, proved that this L sub A map is actually a linear transformation from Fn to Fm. All right. So if you wanted to, you could say that this map psi of A equals to L sub A. This is a bijective correspondence between m by n matrices and linear transformations from Fn to Fm. Okay. All right. Sorry, that's a little bit of a digression over there. So the question then is this mapping here, this L sub T beta gamma. How do we actually calculate that in terms of this picture? So let me suggest the following path. Instead of just going like here to here, we'll do this, like that. So this diagram does it's a commuting diagram. So this red path should be the same as the lower blue path. And so that actually, I mean, it's another way of stating really the definition for that matrix, if you will. Anyway, here it is. So let's see here. Where am I starting? I start with a point here, right? And then, excuse me, I need to go this way, right? So that's opposite the direction of the coordinate map. So I start with phi beta inverse. And then I take T to go from here over to there. And then I finish by going by phi gamma down. So this right here is the implicit definition, implicitly defines the matrix of T with respect to beta gamma. I use this implicit definition to prove a few things about these kinds of matrices. So I wanted to go through this with you so you can understand those proofs better. In practice, this is not how I typically calculate the matrix, right? I showed you an example in the video that you watched, I think. So there's that. That's one thing I need to share with you. The other thing I need to share with you, just a comment about. So if we have T is a mapping from, say, F n to Fm, all right, then what's the, then in that case, we write T of x equals to the standard matrix of T times x. And how do we find the standard matrix? How do we find T? So I explained to you guys, it's T of E1 for the first column, T of E2 for the second column, T of En for the nth column. That's the so-called standard matrix. I don't need the beta gamma here because, well, we're going from column vectors to column vectors, so we can use the standard basis. And also special to this context, I can make some really neat simple statements about the column space as it relates to the range and the null space as it relates to the kernel. So let me just write those down for you guys. What's the kernel of T? It is what? It is x in Fn such that what? T of x equals to 0, right? But if we rewrite that in terms of the standard matrix, what do we have? We have x in Fn such that the standard matrix of T times x equals to 0, right? But what is that? Yep. X equal to 0 is in there, but that's not possibly not all that's in there. This is the set of vectors which, when we multiply the matrix bracket T on that vector, we get 0. This is nothing more than the null space of the standard matrix. So to calculate the kernel of a linear transformation of column vectors, you just calculate the null space of the standard matrix, right? We proved in general last time, or recently anyway, whatever the last time is, I'm not sure. But certainly we have shown that T is 1-to-1 if and only if the what? The kernel is 0. So can a function, can a function be invertible? If it has a non-zero, if it's not 1-to-1? No, I mean, invertible functions, they have to be 1-to-1, right? So one way you could check whether or not T was invertible, if it's a mapping from, say, Fn to F, if it's a mapping from column vectors to column vectors of the same size, if you show the kernel is 0, it's invertible, because that means it's 1-to-1. And by our dimension theorems, it must also be onto, actually. Okay. How about the range of T? What's the range of T? This is T of x, such that x is a column, x is in Fn, right? But what's that? That's standard matrix of T times x, such that, you know, x is equal to, well, x1, x2, xn, right? My point is that what that really is, if you write it out, is x1 times column 1 of T, right? Xn column n of T, am I right? I mean, that's what the matrix column product is. It's a linear combination of the columns of the matrix, right? So what are we looking at? We're looking at an arbitrary span of the columns of the standard matrix. This is actually nothing more than the column space of the standard matrix. How would you tell if a linear transformation from Fn to Fm was onto? How would you tell if it was a surjection? What would we need? So let's see here. 1 to 1, if the kernel of t is 0, right? It's onto if what? The range of t is equal to what? What does it take for this mapping to be onto? The field? The whole thing, right? Yeah, just FM. So it has to cover all of the codomain, right? And in this special context that we're currently in, I can also say, in other words, 0 is equal to the null space, and the column space is all of FM, if I wanted to have it onto. So here's a caution. Caution. The kernel of T is possibly not equal to the null space of the matrix of T beta gamma. And the range of T is possibly not equal to the column space of T beta gamma. So new context, okay? New T down below this line, okay? And here I'm talking about, T from an abstract vector space V to an abstract vector space W. You can't even, those are apples and oranges, right? I mean, like, the kernel is a subset of V, so it could be polynomials. The null space, that's always a set of column vectors. Are polynomials column vectors? No, you can't. These are objects of different type, right? But over here, this kind of tells you everything you need to know. See this right here? This says, we can solve this for T as well, right? T is equal to what? T is phi gamma inverse composed with left multiplication by the matrix, beta gamma, composed with phi beta, like that. If I just solve for T, this gives us this. And because the coordinate maps are isomorphisms, you can prove that this much is true, though. Well, it's not true that these are equal. It is true that these subspaces have the same dimension. So like the kernel has to have the same dimension as the null space of the matrix which represents it, and the range has to have the same dimension as the column space of the matrix which represents it. Because ultimately it's because of this equation. The proof, I give you gory proofs of this on page 180. I don't want to spend our time today on it because I want to make sure I have a bunch of time to talk about the homework. And I think this will help you what I've just said with the homework, though, right? Because a lot of the homework is about, like, is this mapping invertible? Is this mapping one-to-one? Is this mapping onto, right? How do you decide those things? If it's a question about a mapping from like R3 to R2, you can use direct matrix calculation on the standard matrix if you want, right? But if it's a question about an abstract vector space, probably you just need to calculate directly, right? Should we look at an example? Let me not make an example up. Let me let you guys take it over. So you guys got questions? Ask them. If you want, I can put the questions up on the screen. Would that be helpful? Yeah? Okay, let me do that. It becomes important to understand this diagram, by the way, guys. The next topic on the docket is coordinate change. So coordinate change, if you have to really have a firm grounding in what we're doing right now to understand it. So it's important to understand this picture because coordinate change really, that material follows not too difficult. It's not too difficult if you understand the picture. We just add a little bit more to it. If you don't understand this picture, coordinate change gets a lot more mysterious. But anyway, one day at a time. That's in the future. I don't think coordinate change is even part of your mission 5, right? And when's mission 5 due? Wednesday. Woohoo! Let's see here. It's good. I've got more time to work on it, right? Sorry, I will eventually find the statement of this thing. Where'd mission? Come on. Where'd you go, mission 5? There it is. Yeah. That is true. Let's see here. Okay, so, I mean, as far as I know, let's see here. That's way in the future for me. I haven't thought hard about whether or not that makes sense or not, given our current progress. I think we're on track, though. So, so which one do you guys want to talk about? I can try to help you out. This is such a weird idea that you're all confused what's happening right now. I mean, it's... Yeah? 78. So we have basis for each. We defined that to be the unique vector for which that is true. Show that this is a linear transformation. So I can tell you what you need to show. So you want to show that phi beta. So you want to let x and y be in the vector space, right? And c may be a scalar. And you want to show that phi beta of cx plus y is equal to c phi beta of x plus phi beta of y, right? You need to show that that's true, right? That's what we're supposed to show, that it defines a linear transformation. So if I can show that. Yeah. So can anybody help Samantha get started past that point? Like, how to actually do that? What's the nuts and bolts of how this is actually done? What does it mean for it to be a basis? I mean, how do you actually calculate phi beta of something? Here, let me give a specific example. If we had v equal to, say, P2 polynomials with, and suppose that's the span of 1 plus t squared, and 3, right? And if I looked at, f of t equal to, I don't know, 3t squared plus 2, what would the coordinate vector of that be? Well, I have to write it in terms of, well, that's what? That's 3 times t squared plus 0. I'm sorry. I see it now. That's 0 times 1 plus t, right? Plus 3 times t squared plus what? Plus 2/3 times 3. And so there's my first coefficient, there's my second coefficient, there's my third coefficient. So we see that the coordinate vector of f of t with respect to, I didn't even give it a name yet, did I? Beta basis, I'm calling this thing beta, is equal to what? It's equal to the coefficients 0, 3, 2/3, right? And so part of this problem is just to initiate you guys, our other notation for that is just phi sub beta of f of t. I mean, that's just... So this is a very specific example. So this question is much more abstract. So how do I start? I mean, x is in v. What does that mean? X is equal to what? C1 v1, Cn vn, for C1 Cn in f, right? And you can do the same for y, right? So you do that, and you put them together, and then you use the definition of coordinate vector. I can't really write much more without doing it. Other questions? Yeah. All right, well, I'm going to work out an example of a matrix then. So let's suppose we're looking at the linear transformation t of f of x equals to, let's say, f of 0, f prime of 0, excuse me, f prime of 0, and f prime prime of 0. This is a linear transformation. And let's see here. What kind of polynomials do you want to take for your domain? How big? I think quadratic is enough. Yeah? So let's let v be equal to p2, right? And over here, I'm assuming over the reals. So this is apparently, the range is what? W is our 2 by 2. Okay? So to make this problem interesting, we need to, let's do a few things. Let's calculate the kernel of this map. Let's calculate the range of the map. Okay? And let's three things to do. Describe kernel of t, range of t, and find the matrix t beta gamma. Of course, I need to actually tell you what beta gamma are, don't I? So what do you guys want to make the basis over here? How about 1x squared? Sound good? How about our 2 by 2 basis? Let's use the usual one. Let's use 1, 0, 0, 0, and then E12, E21, E22. So the usual lexicographic ordered basis. Okay. So I guess the first order of business here is actually to work out the formula for t, which I'll do over here. Why am I using this? It's not an eraser, it's a smudger. Ay, ay, ay. So my mapping was what? T of f of x equals to, what was it? F of 0, f prime of 0, f prime of 0, f prime prime of 0. That was the map I made up, right? My claim is that this is linear. I won't prove that. It's true, though. So suppose we feed it a plus bx plus cx squared, right? What's the output? So if this is my f of x, which is a generic thing in V, right? A generic thing in the domain, f of x. What do we got? We got A, right? B, B, and not C, but 2C, yeah. Understanding that formula is like the first step. Because that formula will tell us how to calculate the kernel, how to calculate the range, and it'll also be instrumental in finding the matrix. All right. So let's start with the kernel. What's the kernel here? Kernel of t is what? So we're looking at, a plus bx plus cx squared such that what? A, B, B, 2C is equal to the 0 matrix, right? So it's pretty easy to see that that makes A 0, B 0, and C 0. So it's 0. So what can you tell me about the map then, assuming it's linear? It's 1-to-1, right? It's an injective map. What's the range? This is not helping me. One of the points I wanted to make, guys, is like in these homework problems when it says describe kernel or describe, various things, I'm probably most interested in you writing it as a span. That's probably the best way to give the answer. Sometimes I say explicitly find bases, right? Like find a basis for kernel T and range T. So there, you're finding spanning sets which are linearly independent for each thing. Range T, what is it? Well, I would point out that if you go back up to our formula, right? Go back up to our formula, you can rewrite that as what? A times 1, 0, 0, 0. Ooh, I like this marker. Plus B, 0, 1, 1, 0, right? Plus C times 0, 0, 0, 2. Yeah? So apparently the range of T is the span of those vectors, those matrices. So 1, 0, 0, 0, 0, 1, 1, 0, and finally 0, 0, 0, 2. There you go. That's the range. What's the dimension of the range? 3, right. A little bit of a jump there. How do you know that those 3 matrices are linearly independent? How about if you set a linear combination of them equal to 0, it forces the coefficients to be 0, right? In fact, linear independence of these 3 matrices is already almost manifest in the equation I've yet to underline in green. Right? If you were to set this, equal to 0, right? Look at that star equation. If you set that equal to 0, it forces the coefficients A, B, C to be 0. Therefore, those 3 matrices are linearly independent, right? Oftentimes in these kind of calculations, we will actually run across everything we need to prove linear independence of a set, just in the course of the calculation. Okay, anyway. So here we go. There's kernel T, there's range T. How do we find the matrix? Let's see here. So I just figured out that, what was it? T of A plus Bx plus Cx squared was what? A, B, B, 2C, right? Okay, so here's how it goes. We start with f of x up here. Then we feed it to the beta coordinate map. That gives us the coordinate of f of x with respect to the beta basis down here, which, by the way, is just ABC, given our setup, right? On the other hand, over here, we have t of f of x, all right? Which I don't want to write again, but t of f of x is this, right? And then what happens when you look at the gamma coordinate of that? What's the coordinate? So let's see here. This is R3, and our 2 by 2 is a 4-dimensional space, right? So this is R4. What is the coordinate vector with respect to the lexicographic basis of this 2 by 2 matrix? It's just what? I go A, B, B, 2C with respect to the basis gamma, which I've laid out here. Then, to find the matrix of the linear transformation, all you have to do is figure out what do I need to, what multiplies to get from here to over here. And I usually write it out kind of like this. I would say I'm trying to find A, B, B, 2C. That should be equal to the matrix I don't know, right? Which is apparently a what by what? I think it's a 4 by 3 matrix, right? Because we're going from a 3-dimensional space to a 4-dimensional space. that means the matrix is 4 by 3. And you just have to just fill it in. You can see what it is. So I get 1, 0, 0, because ABC multiplied by 1, 0, 0 gives me the A. What's next? 0, 1, 0 to get the B, 0, 1, 0 to get the other B, and then finally 0, 0, 2 to get the last row. And this, guys, is the matrix with respect to the beta gamma basis. It's just that. So to calculate the matrix of a transformation, if you're given the transformation, if you're given a pair of bases, all you have to do is go through this process. You look at a generic element. You have to start with a generic element in the domain. You see what the transformation does to it. All right? Come up with the formula for the image in the codomain. Then you just look at the coordinate vectors of those and see what matrix it takes to multiply to get from one to the other. That's the matrix with respect to beta gamma. Now in the videos that you guys hopefully watched or will watch soon, I also give just a stone cold formula for calculating the matrix directly, much like the standard. I mean, for the standard matrix, we have this formula too, right? Remember that's the standard matrix formula? There's a similar matrix formula here. Like you can say that the matrix of T with respect to beta gamma, what it is specifically is it's T of V1 with respect to the gamma basis. And then the coordinate vector of the second basis vector in beta, the gamma coordinate of that, and so forth. So you can calculate like this as well, and sometimes I do. So this is the other way to do it. If you just want to, if you want to attack the matrix like one column at a time, you can take that approach if you want. Where V1 through Vn are the basis in V. So can I erase over here? So you guys had a couple minutes. Did the question shake loose? We got a question? Yes, Emma. Oh, man. So I need a new battery. Okay, so 81 is the multiplication by complex number problem. Let's see here. Find the matrix. Is it possible to choose some W such that that's the case? That 81? Yeah. It's about, okay, so tell you what, let me look at it. So you're supposed to do it for a generic W, right? Just a second. Oh, man. Oh, man. Let's see here. Come on. Ah! Stop that. It's down here some. Mission 5, right? All right. Okay, so that one. So here what you're supposed to do is to find what the matrix of L sub W looks like with respect to the basis 1i. All right? So maybe it'd be helpful for you if I do it for a specific W. You're supposed to do it for a generic W, right? So you're supposed to do it for something like W equals to, did I even tell you? Like specifically? Oh yeah, A plus IB, right? You're supposed to do it for W equals to A plus IB. But suppose we do it for W equal to 2 plus 3i, just for the sake of discussion, right? So we're looking at L of z equal to 2 plus 3i. Not L, but goodness gracious. What's my notation? This problem? Second here. Apparently L sub w, right? So in my notation, I guess it would be L sub 2 plus 3i if you want me to be obnoxious about it. So this map, left multiplication by 2 plus 3i of z. So what we do is we do 2 plus 3i times z. This is the definition. This is just the definition of the map. So this L2 plus 3i is a transformation that goes from the complex numbers to the complex numbers, and it's defined just by multiplying by a complex number. Is that a linear transformation? Like if you feed it c, it's pretty easy to see that if you did L of 2 plus 3i, say cz1 plus z2, you get 2 plus 3i, right? Times cz1 plus z2, but come on, you can pull the constant out. You've got 2 plus 3i times z1 plus 2 plus 3i times z2, which is to say c times L sub 2 plus 3i times z1 plus L of 2 plus 3i times z2. So I'm not sure that's even needed for this problem, but just so we're on the same page, it is a linear transformation of the complex numbers. All right? So it makes sense to ask what the matrix of this linear transformation is. And the complex numbers, right? So let me, if you don't mind, let me just go on here. So the complex numbers are the real span, right, of, what did I say, 1 and I, right? So we're going to use beta equal to 1 comma I as basis for the complex numbers over the reals. So the complex numbers we can associate with R2, right? Complex numbers are a two-dimensional real vector space, right? Okay, so let's go back to it. So I'm going to look at L of 2 plus 3i. What an obnoxious name for a map. Of z, let's write z as x plus iy, right? That's going to be equal to 2 plus 3i times x plus iy. So right now what I'm trying to do is to find the formula of the map. This is like the step I did in the previous one, and I just erased, like I sorted through the generic element. How does it, so what's a generic complex number? It's x plus iy. I have to see what happens to that under the map. That should reveal to me all the questions I have. I mean, that will be useful as we go on. So, all right, so multiply. This is 2x, right, minus 3y plus I times 3x plus 2y. I don't know about you, but I'm getting really, really tired of writing this. So I'm going to give it a name at this point because I can't suffer it any longer. I'm going to call this L sub 2 plus 3i. I'm going to call it T, okay, for transformation, if that's okay. So, and I'm going to use this as an opportunity to, well, first of all, erase this calculation right above here because it's in my way. I should have done that on a different board if I had half a brain. Oh, well, it's too late. Secret's out. Let's see here. So what's the matrix of T with respect to the beta basis? So I'm giving the basis beta here and here. I'm thinking about the yes, special case, right? If I say just find the matrix of a transformation with respect to just one basis, it must be, for that to make sense, what? That we're talking about a linear transformation from the same vector space to itself, so we give the same basis to the domain and the codomain. Otherwise, the question's ambiguous, right? So that's what's meant here. So I said that should be what? If we follow so it should be T of 1, right? With respect to the beta basis, that's the first column, and then T of I with respect to the beta basis. That's the second column. If I follow, forget about my diagrammatics. If I just use the boxed black formula over there, V1 is 1, V2 is I. What is T of 1? What's 2 plus 3i times 1? Yeah, I heard 2 plus 3i. So 2 plus 3i, the coordinate vector of that. And then we've got 2i minus 3, right? Coordinate vector of that. What is the coordinate vector of these two complex numbers with respect to the beta basis? 2, 3, right? This is minus 3, 2, because I is the second thing and 1 is the first thing. So that's the coordinate vector with respect to 1i basis. I hope I'm not losing you guys with that. So there it is. And you notice actually, did I even use this formula down here? I didn't. Sorry. Well, I could find something to do with that formula, but let me not do that since I'm sorry, guys. I mean, what I wrote down there is not wrong. It's just I didn't use it, so let me just remove it. And so here, the matrix of this. So calling this T, this being my T. Here's the matrix of it, right? What was I supposed to do in 81? I was supposed to find the matrix of L sub W with respect to that basis, right? So then, to see if it's possible, what should I do? How about you could find the matrix of this one, right? Maybe I can help you out with that. What's the matrix? If we define T of x plus iy to be x minus iy, what's the matrix of this? By the way, so I'm just giving you an example. You need to do this not for 2 plus 3i, but for a plus ib. What's going to happen? You'll get a, b, minus b, a, right? Oops, sorry. It's too late. So here this is, again, a linear transformation from C2 to C2, right? The fact that this is a linear transformation, a real linear transformation, follows from the fact that that's complex conjugation. The complex conjugate of a sum is the sum of the complex conjugates. I mean, that is true. Anyway, you can prove that this is a linear transformation. But we'd also like to, let's see here. So we call this thing V. So we're looking for the matrix of T, which I just used in a different sense. I'm sorry. Let me put ones on this one up here. T1, 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 T1. E? Okay. Okay, so the matrix of T with respect to the beta basis times the coordinate vector of V, right, with respect to the beta basis, should be equal to the coordinate vector of T of V with respect to the beta basis. So let's see here. What is this mysterious T beta beta? What's the coordinate vector of V? If this is V, what's the coordinate vector of V? Just xy. Very good. What's the coordinate vector of T of V? What is it? X negative y. Right. So what's the matrix of T then? I heard 1, 0, what? 1, 0, 0, minus 1. Right. So then the question becomes, can you choose a W such that that 1, 0, 0, minus 1 matrix is the matrix of L sub W? Why or why not is that possible? Right? That's the problem. Yeah. If I say any more, I think I've solved it. I may have already solved it. I'm sorry. Giving small hints is not my gift. Other questions? Yeah.
It's not directly from the homework, but
That's fine.
do you have like an example of just finding like the kernel and smoothing things or linear transformation? Just like really general.
Something, finding the kernel of, finding like a kernel on an abstract vector space example.
Yeah, like things that we've done a couple days ago.
Things we've done. Sure. But not on a not on a column vector, but on the abstract case, right? Yeah? No? Probably not a lot. I mean, is there one in here that, oh, it's not, you said it's not like one of these specifically. Oh, by the way, this problem 85, there's a notation here which appears for the first time here. Notice that this T sub W, it's like T restricted to W, except there's no bar. And that's on purpose, because T sub W also changes the codomain. So T sub W goes from W to W, whereas like T restricted to W would go from W to V in this case. Right? So the T sub W, not only it throws out, it like pares down the domain, it also pares down the codomain. Yeah.
So there's
Two typos. Where? Are you talking about grammar? Oh, I don't care. All right. So I will ignore you, as is my right. How this? So T. How about this? T of A is equal to A transpose minus A for A in, let's say, R3 by 3. Okay. Suppose we want to find the kernel of this. This would be a good example, I think, for what you're asking. How would you find the kernel in the range for this one? Is not what you're asking? Oh, okay. I can't tell. So if we look at this, what can you tell me about this? What's the transpose of that? Right? Wait a minute. Just a second. Oh, so this is, yeah, okay, so that's minus A transpose minus A, right? So apparently the range of, what's the range of T here? Can you describe it in words? It's B such that what? Well, I mean, I guess I don't know it's all of this, but it certainly is a subset of the antisymmetric matrices, right? Okay. All right, but this gets us so far. Let's actually do it. So if I take A equal to A, B, C, D, E, F, G, right, HI, and I take the transpose of that, so that minus A again, right? That's T of A, right? So we could write that as what? This is equal to A times what? Well, is there an A actually? No, the A pieces cancel. What cancels? Let's just do that in red right quick. That's the A, the E, the I. E's are gone. D, how about D? What's D left with? D times what? Times E11, excuse me, 1, 2, right? E12, and over here, minus E21. And plus G times what? Times E13 minus E31 plus H times E23 minus E32. And that's it, right? So what's the kernel and what's the range here? I mean, you should be able to see the range from this formula. The range of T is in fact the antisymmetric matrices, because these form a basis for antisymmetric 3×3 matrices. We've seen that before. Okay, so range of T is the antisymmetric 3×3s. What's the kernel? The kernel is pretty easy to, kernel is considerably easier to calculate, right? What's the kernel of T? We're looking for A such that what? Such that A transpose minus A is equal to 0, yeah. So apparently the kernel is the symmetric matrices, right? Symmetric 3×3s. So the kernel is the symmetric. Which I could write as the span of the you know, E11, E11, E22, E33, and then rather than differences, the sums of these guys. That would be a basis for the symmetric 3×3 matrices, which is 6-dimensional here. It's not an accident that the range is 3-dimensional and the kernel is 6-dimensional here, because the domain is 3×3 matrices, which is 9-dimensional over the reals. This always happens, actually. The dimension of the domain will equal the dimension of the range plus the dimension of the kernel. This is the rank nullity theorem. If you go back and look at all of the examples, this is very, very easy to see, and it's actually clarifying as you calculate. Look for this. The rank nullity theorem will guide your calculations. You should always have that the dimension of the column space plus the dimension of the null space is the number of columns in the matrix, for example. That seems like, how do you prove that? Well, it's because the dimension of the column space is the number of pivots. Dimension of the kernel is the number of non-pivots. So what's the total number of pivots plus non-pivots? It's the number of columns, right? So this theorem doesn't seem like it's that deep, and yet when you apply it to examples, it's very clarifying, and it'll save you calculation depending on how you're asked questions. Yeah? Anyway, I don't know if that's helpful or not, Bethany. It's all I can eke out here in 3 minutes. Wait a minute, 7 minutes. Brevity is the soul of wit, right? So go figure. Thanks.